All right. So welcome back to your favorite inorganic tutor YouTube channel. Today is another episode. We want to look at how we can use the Gauss-Jordan method to solve three systems of equations, right? Now, I want to give you a brief history about Gauss-Jordan, right? This Gauss started the process. He actually ended on the upper triangular matrix, right? He ended on the upper triangular approach so that after you finish the upper triangular, you do back substitution to get the solution. But this guy went ahead, Gauss-Jordan went ahead to finish the lower triangular matrix so that you can just get your solution right away from the matrix. So what he did was that he added more work. He added more work. So, this matrix itself can be traced back to um, Carl Friedrich Gauss. He is the man of matrix, right? He started the work of matrix. So everything has to be attributed to him, right? And he actually lived about 78 years on this earth from 1777 to, I think, 1855. That was his lifespan on this earth. So the origin has to be traced back to Friedrich Gauss, right? He is a German mathematician who really made a significant contribution to linear algebra and numerical analysis in uh, real life, right? So, Gauss didn't necessarily familiarize himself with the method in its modern form because his work in solving systems of linear equations and his contribution to the theory of matrices laid the foundation of Gaussian elimination to also proceed on that. So Gaussian elimination, which often called the row reduction, is a method for solving systems of linear equations by transforming the matrix or the augmented matrix, right? He will transform the matrix into augmented matrix of the system into an upper triangular matrix, right? Then this will allow you to do back substitution when you are done with that to solve for the variables, right? But Wilhelm, I think Wilhelm Jordan, he also lived around 1835 to 1921. That was his lifespan. And then he also contributed to these matrices and stuff. So the Gauss elimination method was familiarized with him also, right? So Gauss extended the Gaussian elimination process by introducing an additional step, and that is the reduction of the matrix to a reduced um, form, a reduced row echelon row form, reduced row echelon row form, and that is the RREF, reduced row echelon form. He did that process so that you can get your solution right away from the work. So the main difference between the Gaussian elimination and the Gauss-Jordan elimination is that whole while Gaussian elimination was what steps, or he stops at the upper triangular form, that is the row echelon form. Gauss-Jordan elimination went ahead, or he went further to obtain the reduced row echelon form so that you can get your solution right away from there. So the impact and uses of Gaussian elimination is actually um, one of the major advantages of Gauss-Jordan elimination, and it is an ability to the matrix uh, compute the matrix, right, distinctly or directly if the matrix is invertible. Invertibility means you have uh, a determinant not to be zero, because if you have a determinant to be zero, you have the matrix not to be invertible, right? So he also contributed to the systems of linear equations. Both Gaussian elimination and Gauss-Jordan method is widely used to solve systems of linear equations, and it can be applied to both square and non-square matrices. Though non-square matrices might have a solution or might have infinitely many solutions. So this guy really had an impact on matrices. So today we are going to look at some computations on how we can use the Gauss-Jordan approach to solve these three systems of equations, right? So first, what we have to do is that we have to transform these three systems of equations into an augmented matrix, right? So augmented matrix, all we mean is that we write the coefficient of the variables. You know, we have one coefficient of x right here is 1, 2, 1, and then 2, 3, 3, and then we have 1, 1, 1, right? Then we augment it with the constant. So we have 9, 21, and 10. Right? So this we have right here, we have augmented it. So this is the augmented matrix for these three equations. So what we do next is that we make sure that the leading first element is 1. And this right here is 1 already. So we don't have much work to do, or we don't have any work to do. What we do next is that we make the first element of the first row a leading one. And that is what we have right here. So we don't need anything to do right here again. So we first have to eliminate the first element of the second row and then the third element of the right. So this is how the process goes. You know, matrices really appreciate order. So normally people are not taught how to start the elimination, so they just start it from anywhere and they get it wrong. But I want to give you a big secret, right? This right here, we start from here. You know, we are eliminating the upper triangular, right? So we start from the second element, the first element on the second row, right? We start from that point, we move down. You know, this one is in a particular direction. We are not just moving to this, then we jump to this part before we come here. When you start from the second element, the first element on the second row, make sure you move in that direction. So you move to this way. You don't move from here, go here before you come here, or you move from here, come here before you go here. No, it doesn't work that way. Always make sure that you move in this direction. And also the upper one goes in this direction as well. Don't move in any other direction than this. That is how you get it done easily. It is very simple. So move here and come here. So we are coming to start. We want to make this element right here to be a 0. So what do? We stand on this, then we use this rule, the rule 1, right? So we say that rule 2 should be equal to rule 2 minus 2 rule 1, right? We can see that when we maintain this minus 2 times this, we are going to get 0 right here. So let's go. We maintain the first row, 1, 2, 1, 9. Then we have 2 minus 2 times 1, and that is 0. And then we have 3 minus 2 times 2, right? And that is minus 1, right? And then we have 3 minus 2 times 1, and that is 1, positive 1, right? And we have 21 minus 2 times 9, right? So we have 21 minus 18. right? And that is 3, right? So we have here to be 3. So we have the next element come 1, 10, right? So now we are done with the first element on the second row. We move down to the first element on the third row. So we are interested in eliminating this particular one, this one right here. So what we do is that we say that equation or row 3 should be equal to row 3 minus row 1. You know, when you subtract this from this, you're going to get 0 right here. So we have this, right here. 1, 2, 1. Then you maintain this here. Then you have 1 minus 1, and that is 0. Then 2, we have 1 minus 2, and that is negative 1, right? And then we have 1 minus 1, and that is also 0, right? And then 10 minus 9, that is 1, right here, right? So the next thing we have to do is that we have to eliminate this minus 1. So what do? We have to make sure that it has the first, it has a leading one. The third row has a leading one. So you have to make sure that this particular one tends to positive 1. So we multiply through by negative 1, right? So when we multiply row 3 by negative 1, then we are going to have 1, 2, 1, 9, 0, neg 1, 1, 3. Then we multiply the row 3 by negative 1. So we have 0, 1, 0, neg 1, right? Now, we want to eliminate this particular one. So what do? We say that now we have stand on the row 1 to eliminate this. So we don't need to stand on row 1 again. So we have to move down to row 2, right? We have to move down to row 2 and then use row 2 to eliminate row 3. So we say that row 3 should be equal to row 3 plus row 2, right? Because you know that when you add this and this, you are going to get 0. So we have 1, 2, 1, 9, 0, neg 1, 1, 3. Then come down here, 1 plus negative 1, and that is 0. 0 plus 1, and that is also 1, right? We have negative 1 plus 9, negative 1 plus 3, and that is positive 2. That is positive 2. So what we do next is that we are now we are done with the upper triangular matrix, right? So this guy, Gaussian elimination, he ended here. So you have to do back substitution to get the values for the variables. But Gauss-Jordan went ahead to eliminate the top element to that is the lower triangular matrix as well. So let's go ahead and eliminate this, eliminate this, eliminate this. Meaning we are making it 0, 0. So if you want to make this 0, where do you start from? You stand on this, then use this one to eliminate it, right? So we can say that row 1 should be equal to row 1 plus 2 row 2. Row 1 plus 2 row 2 is going to give us 0 right here. So we have this here. We have to maintain the second and the third row. Right? So we are maintaining the second and the third row. So we have 1 plus 2 times row 1, and that is 3. 1 plus 2 times row 2, row 1, which is 2, plus 2 times row 2, right? So right here is 1. So let's have this here. So we have 1, the 1 here, plus 2 times row 2, which is 0, right? So we still maintain the 1 right here. And then we have 2 plus 2 times -1, and that is 0. So we have eliminated these 2 right here. So we move to this. We have 1 plus 2 times 1, and that is 3 right here, right? So we left it the constant aspects. We have 9 plus 2 times 3, right? And that is 9 plus 6, and that is 15. So we have 15 right here, right? So the next we do is that we eliminate the next element, which is the 3, right? So we have to use this. We can use this to eliminate it, right? So we can say that rule 1 is equal to rule 1 minus 3 rule 2, right? Rule 1 should be equal to rule 1 minus 3 rule 2, right? So we have right here, we maintain the right. So now let's move to by eliminating this, right? So now we want to eliminate this 3, right? So we say that row 1, which is 3, minus 3 times row 2, and that this part will give us 0, right? And then 3, this one, 15 minus 3 times 3, right? So we have 15 minus 6, and that is 9, right? So we have 9 right here. We have 9 right here. So we are left with the last element to eliminate, right? So we have to eliminate this number right here, right? So what do? We can say that this row, which is row 2 minus row 3, will give us 0, right? So we have row 2 should be equal to row 2 minus row 3, right? So we are going to have 0, neg 1, 1, 0, 0, 1, 3, 2, and then we have 1, 0, 0. So let's come up here. Right, so we have row 2 is equal to row 2 minus row 3, right? So when we do that, we are going to have row 2, right? So row 2 minus row 3, right? So we are going to have right here root 2 minus root 3, right? So we have 2 minus 0 minus 0, and we have 0 right here, and then 1. Let's maintain the necessary parts where we are not going to touch, so that we proceed to right. So right here, so we have root 2 minus root 3, right? So we have 0 minus 0. We have 0 still maintaining, right? And then we have negative 1 minus 0, and that is still negative 1, right? And then we have 1 minus what? 1, and that is 0 right here, what we are interested in. And then 3 minus 2. 3 minus 2 is positive 1, right? So what we have to do right now is that we have to make the first element, the element on the second row, we have to make this element, the second element on the second row, a leading one. So what do? We multiply through by what? Negative 1. So multiply root 2 is equal to negative root 2, right? So we multiply root 2 by negative 1. So we are going to have this right here, 1, 0, 0, then our 9, then 0, 1, 0, 1, negative 1, and then 0, 0, 1. Then we have 2 right here, right? Very, very simple. You know, what you have to consider the most is that you have to respect order for the matrix, because if you jump from this side to this side, anywhere you like, you get it wrong right here. So we can see that the value for the variables x and y can be notified right from here. We can see that x is 9, y is negative 1, and z is positive 2 right from here, right? So we can see that therefore s is equal to 9, y is equal to negative 1, and z is equal to 2, right? Very, very simple. But I want to stress on this thing again, right? I want to stress on this thing again. Let me write this and stress on it again. When you have something like this, a 3 by 3 or anything, G H augment it with right. So when you augment it and you want to use either Gaussian elimination or Gauss-Jordan method of elimination to find the values of the variables, what you have to make sure you consider the most. I know this thing is something that is supposed to be known, but we are not told, or they don't tell us, right? So always make sure that you follow this order. From here, then you come down here, then you move to this part. Don't jump from this part, then you come here, then you come here. No, it doesn't work like that. You know, matrix really appreciates order. He respects order. Gauss really respects order. So he makes sure that when you start from second row, you come down to the third row, the first element on the third row before you move to the second element on the third row. You can't start from the second element on the third row before you come to the first element on the third row. No, Gauss doesn't appreciate that. Likewise, when you come here, it starts from the B, move to the C before you come to F, right? But don't do this. Don't start from here, move to this place before you come here. No way. Don't do that. Always make sure that you follow or you respect order of matrices. Move from a respected row to the next in that order. So thank you very much for watching. I really appreciate your time. Next time, I'm going to upload how we can find the eigenvalues and eigenvectors of a 3 by 3 matrix. Thank you very much and bye.